Magnetic Fields Part 3. We are trying to show that Ampere's law and the Biot-Savart law are the same thing. And if you think about it, they are. They both relate current to magnetic field. Because electricity and magnetism apparently are connected. Electric fields and magnetic fields, are they the same or different? Well, the similar parts are the same and the different parts are different. But how can we be precise about the difference between an electric field and a magnetic field, its shape? Well, in order to do that, we'll need vector calculus such as Stokes Theorem. The closed integral f dl is equal to the closed integral of upside down triangle cross f dA over a closed area. With a counterclockwise convention, here is a different notation. But what is this upside down triangle? It is the del function. It's an operator. It looks kind of like a vector, but it's an operator. D dx in the x direction, d dy in the y direction, d dz in the z direction. And it operates on functions like this one doing that. That's the gradient. It tells you how your vector field is changing. Or with the dot product, the del function or operator gives you the divergence of the vector field, and the cross product gives you the curl of the vector field. Just one question. What's a vector field? It's this. All sorts of arrows pointing in different directions, moving around through space. Sometimes they're growing, sometimes they're shrinking. You can show that by making some bolder than others. This vector field is different than that vector field. But we should really be talking in 3 dimensions, although that gets kind of messy unless you have a very boring vector field like this one. A constant magnitude and a constant direction to the right. Think of it as constant velocity to the right. Or how about this? Think about this as the electric field between the parallel plates of a capacitor. Constant magnitude and constant direction. Here's the question. Could your vector field do this? Could it increase in magnitude? Well, not if it's the electric field between those plates of the capacitor, not without some other charge there. How about if this represents a bunch of people walking and then they all start to run? Yeah, that would be possible. And as they ran, the people would spread out, the density would be less. That could not, however, happen if this was the vector field for fluid in a pipe. You couldn't have the water just magically speed up at some point. So what I'm trying to say is what type of vector field you have depends on your physics. And describing it is the job of vector calculus, including the gradient, divergence, and curl. Let's take a look at the gradient first on a very boring vector field. A topological map, contour lines. What we have is altitude information for all these different points. Again, this is very boring. Instead of a 3-dimensional vector field, here we have just a 2-dimensional scalar field. 2 dimensions. Latitude and longitude, and a scalar field. I have an altitude value for any location on the map. And now I can take the gradient of this field to find out where I want to go sledding. Would that be a good place to go sledding? No, it's got a high altitude, that's true. But sledders don't care so much about the altitude as how the altitude is changing. That would be a better place to go sledding. That has a big slope, you could say, at least in the y direction. And we could use the gradient on an electric field like this. It could tell us where the electric field is getting stronger or weaker. That might not be as interesting, however, as taking the divergence. Well, so let's take a look at divergence, which uses the dot product, which uses the cosine, which tells us about the parallel component. We use the dot product to find the work done by a force. The divergence tells you about how you change in the direction going away. A positive divergence means that your vector is changing, it's increasing in the direction that it's going, so it's diverging, for lack of a better term. Just think parallel components, not like the curl. That uses a cross product or the sine function, perpendicular components. We use the cross product to calculate torque or turning force. So if the divergence tells you if you're speeding up, we'll say the curl tells you if you're turning. First divergence, like this field here. Something exciting is happening, maybe not so much there, but something definitely exciting is happening here. This might remind you of Gauss's law and the electric field around a point charge. Here we have a smaller sphere and a stronger electric field, a larger sphere, a weaker electric field. The farther away from that point charge, that makes Gauss happy. The div function does sort of the same thing, but again, the div function is more interested specifically in how those vectors are changing. Notice the farther away you are from that point charge, the smaller the change per delta x of your vector strength. Still, you can integrate over a volume to make Gauss happy. Next, we'll consider the curl and the cross product. This vector field might look like the magnetic field for a current-carrying wire coming straight out of the screen. A small circle, a stronger magnetic field, but again, the curl is more interested in how those vectors are changing. Each arrow is perpendicular to the one before it. A bigger circle. Here, the change in direction is not as drastic. Still, in order to make Ampere happy, we can integrate the curl of this field over that area. Stokes Theorem. A quick and dirty introduction. Because vector calculus is our way of describing the difference between electric fields and magnetic fields and how they look and how they work. All right, back to Ampere's law and Stokes' theorem and our next step, which involves the current density. If you're wondering where area came from there, J is current density, current per area. The curl of B, or del cross B, is equal to mu naught J. Which is a good time to remember a fun fact about magnetism. Div B is 0, which means you cannot have an isolated magnetic pole. Here's something else. A vector, if you're taking the cross product, A needs to be a vector. We'll call it the vector potential. And if you're thinking curl A has to do with current or electric field, therefore A has something to do with the integral of the electric field, which is voltage or a vector voltage. Something like that. One last fact, if we defined A to be anything we want it to be, and apparently A has something to do with electric field, we can insist that the div of the electric field is 0. In other words, no charges at that point. Let's get moving with a fun fact about vector calculus. And if that looks bizarre and mysterious, it is. We got it from a textbook, just like we learned geometry and then got facts from a textbook, and then trigonometry and got facts from a textbook, and special integrals from a textbook. The cross product and the dot product are the same way, and so are vector calculus. And here is that fact that we are using, so let's use it, and let's remember that neat thing we insisted about vector A to write Poisson's equation. And if del looks like a vector, it's really not a vector, it's an operator. But if del kind of looks like a vector, ddx, ddy, ddz, then del squared is the second derivative. And now the magic happens, because Poisson's equation can be solved using the Fourier transform. I have a series of videos, get it? A series of videos on the Fourier transform, Paris and the cosine, and that's just mysterious to me. But then I found another presentation that talked about this function called Green's function of the Laplacian, and applying the Laplacian on Green's function produces a three-dimensional delta function. Anyway, this is the step where the magic happens. If you have a better conceptual explanation of this step, please let me know about it. I'm all ears. That gives us an equation for A, but we wanted B. Oh yeah, B equals curl A. We defined that. And the curl gives us a derivative. We assume current and current density are constant, but curl gives us a derivative. J over R becomes J over R squared. Negative indicates direction, and we're getting very close now, but we have B in terms of J. Remember the relationship between current density and current. Divide by area, integrate over area. I apologize for all the hand waving. This has been the most hand waviest demonstration that I have ever accomplished here, but hopefully I was able to sneak in an introduction to vector calculus, which we can use to explain how electric fields and magnetic fields look different and are different. And if you're feeling like this doesn't quite tell the entire story, you're absolutely right. That's Maxwell's equations, and that's coming up soon. Next, though, one last attempt at showing that Ampere and Biot-Savart are the same sort of thing.